Give a dark Pennsylvania ringing rock the lightest tap the site allows, and a metallic note can hang in the air like a bell. Tap the boulder beside it, and the sound may die in a blunt thud. The two stones can look almost identical. If you want to see what happens when this mystery is tested, subscribe to Gen Movie. Then, in the 1960s, researchers put the ringing rocks under a saw. The dull samples stayed dull. The ringing samples expanded slightly over roughly 24 hours and went silent. The blade found no bell inside. So what did it release? That opening tap belongs only at a site where current rules expressly permit it. The saw belongs to a historical experiment, never to your field kit. The mystery sits in the vibration itself. Why does it survive inside one solid rock and collapse inside the next? Stand between two dark boulders, and the contrast can feel impossible. One answers with a clear note that lingers. Its neighbor swallows the same light impact almost immediately. Researchers later used simple names for that split. The musical rocks were live. The dull rocks were dead. Those words described acoustic behavior, nothing more. The first useful clue is duration. A live boulder allows vibration to persist long enough to reach your ear as a recognizable tone. A dead boulder damps that movement much faster. Loudness can change with force, shape, contact, and where the rock is struck, so the cleaner comparison is how clearly the note forms and how long it survives. That distinction already kills one popular shortcut. A metallic sound does not prove the boulder contains metal, valuable ore, or a hidden bell. It tells you that the whole object is vibrating in a particular way. But three tempting explanations remain. Maybe the rock is hollow. Maybe iron creates the tone. Maybe the boulder pile holds each stone on perfect natural supports. One experiment forced all three ideas into a much harder test. Rutgers University, the 1960s. John F. Gibbons II and Stephen Schlossman separated diabase samples into live and dead groups by sound. Then both groups met the same blade. The dead rocks stayed dead. Sawing caused no notable change in their sound or volume. They were dull before the cut and dull afterward. A fresh surface did not wake them up. The blade did not expose a chamber that suddenly made them musical. Nothing important changed. The live rocks responded in the opposite way. Once the blade opened a ringing sample, the cut material expanded slightly over roughly 24 hours and lost its ringing ability. The live samples were also less weathered. Those are the observations that matter. The rock changed after the cut, and the clear metallic note disappeared. The timing makes this more than a strange cutting story. Nothing was pulled from the boulder and held up as the source. No little bell fell out. No hidden object had to be named. The important change happened to the cut rock itself, and the consequence arrived as silence. Put the two groups side by side. The same intervention left the dead material acoustically unchanged, but the live material expanded slightly and lost the trait that had defined it. The saw did not reveal the ringing condition. It erased it. That reversal points toward the physical state of the entire boulder. The leading explanation is retained internal compressive stress, forces held inside the solid rock and distributed through its interlocking minerals. A light impact starts vibration. When the boulder retains the right internal condition, that movement can continue long enough to produce a clear, sustained note. A guitar string gives you a rough picture, but only a rough one. String under tension carries a note differently from a relaxed string. A diabase boulder is not a wire, and compression through a complicated mineral mass is not the same as tension along a string. The comparison only shows how stored mechanical stress can change the survival of vibration. The slight expansion after cutting fits stress release. The lost ringing fits it too. The unchanged dead rocks sharpen the case because the blade did not create the same response in every sample. Internal compression therefore leads as the explanation for the tested live rocks. But the experiment gives a direction, not a complete map. It did not measure the exact stress in every mineral grain or explain every pitch. Cracks, mineral fabric, shape, size, support, contact, and weathering can still affect how vibration travels and fades. The evidence supports a mechanism without turning it into a universal law for every ringing stone on Earth. Now return to the three tempting explanations. An older proposal pointed to an iron content of roughly 9 to 12%. Iron-rich composition may influence acoustic behavior, but basalt and gabbro with broadly similar composition do not automatically ring. Iron alone cannot explain why one diabase sample is live, while another is dead. The boulder field can also tune a note without creating the whole phenomenon. Support, contact, size, and shape affect the sound of a particular block, just as the supports under a xylophone bar affect its response. But ringing boulders retained their ability after being removed from their original positions for testing. The special arrangement of the pile was not enough by itself. A hidden cavity is unnecessary for the same reason. The live quality survived movement but disappeared after cutting, while the dead material ignored the blade. That pattern keeps bringing the answer back to the whole solid boulder, rather than something concealed inside it. These Pennsylvania boulders are diabase, a dark mafic igneous rock built from interlocking minerals. Other naming traditions may use dolerite or microgabbro for the same broad material. Diabase identifies the rock. It does not promise music. A dull neighbor can share the same broad composition and origin as the stone that rings. The word sonorous simply describes a rock that produces a tone when struck. That label causes another naming trap. Sounding stones are sometimes loosely called phonolites because the word suggests music, but formal geological phonolite is a different volcanic rock type. Pennsylvania diabase does not become phonolite because it rings. The shared story of these boulders reaches back to the breakup of Pangaea, beginning roughly 220 million years ago. Molten material intruded below the surface and cooled into diabase. Long exposure, weathering, and repeated freezing and thawing later helped break once-connected rock into a boulder field. The same geological history produced the broad material, but it did not preserve the same internal condition inside every block. If you like field science that separates what a rock actually shows from what a myth claims, subscribe. The live rocks still leave one practical question. How do you compare them without turning the test into damage? Back across the boulder field, weathering may be producing a slower version of that stress release. It may gradually help a live boulder lose the stress that supports its note. The live samples in the cutting comparison were less weathered, which fits the leading explanation without creating a clock for when any one rock will go dull. The complete mechanism remains partly unsettled. That uncertainty tells you how far the evidence reaches. Ringing Rocks Park in Upper Black Eddy, or at any public site with sonorous stone, read the current signs before touching anything. Public access does not grant permission to collect, chip, drill, cut, smash, or remove rock. If light tapping is expressly permitted, choose stable footing, stay off loose boulders, and keep your hands out of gaps where shifting stone could trap them. Wear eye protection, because even a permitted light strike can move a small chip. Avoid loose fragments, thin corners, heavily weathered edges, and unknown mineral specimens. Use the smallest permitted tap on a stable face. You are listening for clarity and duration, not trying to force the loudest possible sound from the field. Move to a nearby candidate, and repeat the action with similar force. A live rock should answer with a clearer note that hangs longer. A dead rock should stop sooner, with a dull response. If the first candidate stays quiet, do not hit harder. More force increases risk and ruins the comparison by changing the action. Choose another permitted candidate, or let the question rest. A phone recording can help you replay the notes and compare how they fade. It cannot identify diabase, measure internal stress, prove a cavity, settle the mechanism, or give you permission to take the stone home. The microphone is a listening aid, not a laboratory. Keep the comparison narrow. Similar force lets you compare the rocks instead of comparing two different swings. Listening for duration keeps attention on the ringing quality instead of raw loudness. Leaving every boulder in place protects the site and preserves the physical condition under discussion. If signs prohibit tapping, stop. If the boulders are loose, your footing is uncertain, or the only reachable surface is a fragile edge, stop. The historical experiment already supplied the destructive test. Repeating it in the field could damage the object, violate the rules, and erase the very condition you came to understand. The live versus dead split gives you a clean interpretation. A metallic note is evidence of sustained vibration, not hidden treasure. A dull neighbor may still be the same diabase. Iron, shape, support, contact, and weathering can influence the response without explaining the entire contrast. The strongest clue remains what happened under the saw. Dead samples stayed dull. Live material expanded slightly and lost the note. Retained internal compressive stress leads because it connects those results without claiming more than the rocks showed. Sawing may give that stress a route to relax, Weathering may work more slowly. Other differences still matter, and another sonorous rock site may not follow the identical pattern. The uncertainty tells you exactly where observation must stop. Return to the dark boulder. One permitted light tap leaves a bell-like note hanging over the rough diabase, while its neighbor gives back a thud. What sounds like a hidden bell is the whole rock holding vibration. Leave the live boulder where it is. Break it to find its bell, and the bell can vanish with it.